And indeed, I want to talk about virtues of patience in strategic queuing systems. And this is joint work with Jason Gaitonde, who is a graduate student at Cornell, but actually currently interning at Microsoft. So I guess not as good as I imagined. Sorry, I'm having some technical difficulty here. Hopefully can solve it. Excellent. Okay, so we consider the price of anarchy style question, that is interacting selfish agent or a game, and ask how good the outcome is. And the price of anarchy has been historically meant to measure the worst case between selfish outcomes or maybe Nash equilibrium and a social optimum, but classically it was a Nash equilibrium. And then you can ask yourself, you know, how do people find this Nash equilibrium? And actually, maybe what I'm more asking is that many games are played over and over again repeatedly. And what does this say in games which are getting played repeatedly? So by repeatedly playing, I need something like this picture that you play the same game over and over again. And there are many examples of this. Bidding in auctions is kind of like this. Package routing also kind of like this. I guess a simple behavioral assumption that has got a lot of attention is no regret learning or Hanan consistency, where the behavioral assumption would be that you should do at least as well as any single action would have done with hindsight. This has large literature and maybe sort of two big benefits. There are many simple and efficient algorithms that actually achieve Hanan consistency. That is a simple algorithm that a player could play that guarantees that they do at least as well as any single action with hindsight. And in any case, this assumption that everyone does at least as well as any single action with hindsight is at least as good, that is better than assuming that the players somehow reach a Nash equilibrium or a single shot game and then keep repeating it. Effectively, it's that assumption without the assumption of stability, that it's the same action they're playing over and over again. And again, it has algorithmic advantages. Coming from the price of anarchy literature, so price of anarchy started with the work of Koutsoupis and Papadimitriou, asking this question, and there is a long line of literature. I'm only citing here very early works and very few of them, but maybe the message that I wanted to get to, that these results often or almost always extend to no regret learning outcomes. That is, if instead you assume, instead of assuming that the players reach a Nash equilibrium or somehow magically find one, you're assuming that it's a repeated game and they repeatedly play it and each of them satisfies the no regret property, then the same quality bands do apply, by which I mean they can reach a Nash equilibrium or maybe not, but as long as they satisfy this simple behavior assumption that each of them do at least as well as any single action with hindsight, then the quality bands do apply, which maybe makes you think or makes one think that the no regret learning was the right form of learning in some sense. And I guess what I'm going to do in this talk, in a way, analyze a game and then somehow have the message that, well, maybe it wasn't the right form of learning. And I guess one critical assumption in all of these results that are referenced here that extend things to no regret learning outcome is not only that we played the same game over and over again, but that this game has a simple form in which there is no carryover effect between rounds of the game, except that players are learning. So they're learning from what happened in previous rounds, but beyond that, the game is completely unaltered. So I guess the question we're asking, or maybe complaining, is this a reasonable assumption? And I guess I want to start with convincing you that no, of course it's not reasonable. So some situations it's reasonable, and I guess the contrast that I like putting up is traffic routing, where one version on the, I think, left side of my screen is morning rush hour traffic, and the right side of the screen is a very schematic picture of the internet packet traffic. But if you want, there could also be rush hour traffic. It's just the minute by minute traffic rather than the morning by morning rush hour traffic. And I guess in the morning by morning traffic, this is a reasonable assumption. No matter how bad traffic was Monday morning, you know, other than unbelievable disasters, by Tuesday morning, those cars are all gone. And other than your memory of what was good and what was bad, it's a new game. But on minute by minute traffic, it's not true, because, you know, when there are lots of packets or lots of cars in a road, then 10 minutes later, most of them are still there. So there is a definite carryover effect. And this is the kind of thing Jason and I have been working on for the last couple of years. I claim that repeated games where there is some stateful system, that is the state of the system evolves as you play the game, is much less well understood, as in not so understood. Jason and I had a paper in EC20, and I actually gave a talk about this at Stony Brook a year ago. Exactly the same game I'm studying here, and I will tell you a little bit about this. And in that paper, we've made the behavioral assumption that all the players are playing no regret learning. And we proved some positive results, that with enough capacity in the queuing system, it's going to work out okay. And basically what we want to show is that this no regret behavior is myopic, and if they actually were to play the Nash equilibrium of that game, they would do better. But without going into the details now, let me actually spend a couple of slides telling you what the game is, that is, what the actual game that we're studying. So this is a very simple version of a queuing system. There are multiple queues, and those going to be the players, and there are servers that the queues can go to get service. The queues get packets. Each queue gets a packet with some random rate of Bernoulli process with rate of lambda I for qi. And then each queue needs to choose a server to send its packet to, and the servers are a bit different. Maybe they each have a ability to serve with some probability mu j. Server j will be actually successful in serving a packet. And each time step, each queue can send one of its packets and sending it to one of the servers. Okay, so this is going to be a game, and you will have, as a player, you have some funny trade-offs to think about. If a server is very popular, everyone's sending there, then trouble is it's probably going to serve someone else's packet and not yours, or that certainly might be the case. If it's a bad server, then, well, you might get served, but then again, maybe but try to serve, but it's a bad server, it might fail. So what happens after a round like this, the server can process at most one packet. Some servers fail and send the packets back. Some servers succeed. For example, the upper server succeeded, but there were two packets there. It succeeded with one of them.
What does a queue condition its decision on? What can it observe?
Excellent question. I'll come back to this in a tiny second. One thing I should tell you before even answering your question is, how do the servers decide which packet to serve? So I'm going to make the assumption, and I can come back to this in a Q&A of why this is a reasonable assumption, that packets are time-stamped, and they're going to make an attempt to serve the oldest packet. Like it's something trying to be fair, and the oldest packet is the most needy, and that's the one it's going to serve. Okay. So that's the model without elaborating on who observes what. And I guess I don't have a slide talking about who can observe what, but maybe we're sort of thinking about what are the options of what a queue can observe. One thing a queue definitely observes is its success rate. Like, you know, is the packet coming back or is it not coming back? That's a super easy thing to observe, in fact, and no matter how I set up the system, that is something that queues observe. And at least in the positive results you have, this amount of observation is enough. You can ask yourself the question that if I give you more information, for example, I can let you see who else sent to that server and who got served, or how old was the packet that gets served. Then, you know, does it help you? Is it better? And in fact, if the question will be the first version, that is the using learning, then with this extra information, you surely will learn faster. So the ultimate limit result is not going to change, but the speed at which you can learn to do the right thing will actually get affected with how much information I'm feeding you. The Nash equilibrium question I'm asking will not be dependent of how much information I'm feeding you, but in any event, the bare minimum information, you see whether your packet came back. That's an important fact, and you definitely need to see that. So I like again, the line of work here is the sort of price of energy style analysis. So before I can do that, I have to somehow measure the optimum. That is, I know I can ask, suppose I can coordinate, I can get this centrally designed optimum, what can I do with that? And for that, I guess it's not very hard to sort of think about how one arranges it. And I guess just as a notational convenience, one can say, can assume notationally that both queues and the servers are sorted in quality order. That is, the earlier queues have higher arrival rates and the earlier servers are higher service rates. Again, this is a notational assumption, not a knowledge assumption. With this assumption, the following condition is necessary and sufficient if you're willing to coordinate. That is, if I take the top k queues, some number of queues, then remember each server can only do one thing at a time. So if I coordinate well, they can send to separate servers, and those servers should have enough joint capacity to service this queue. If the arrival rate is bigger than the service rate, then obviously I won't be able to serve all those packets. If it's strictly less, then apparently I will be if I coordinate very cleverly. Again, so I guess a simple version is that the highest arrival queue rate should have less arrival rate or smaller arrival rate than the best server. The first two queues should have less than the first two servers, and so on. It's not very hard to prove this, and it certainly feels like a natural, obviously necessary. Not very hard to prove that it's sufficient, and it's obviously a necessary assumption. So what I'm going to ask in the price of energy style setting is how much more capacity do I need if instead of centrally coordinating, the queues are themselves coordinating or combining in some way. So I guess the early paper had this result. If they're running a no-regret algorithm, you need double the capacity. So if the top K queues have enough capacity, top K servers had enough capacity to effectively service these servers, even if they had double rate, then even if they're playing no-regret algorithms, they will actually get serviced using no-regret algorithms. That is, the queues, the backup on the queues will not grow linearly. I will not show this, but turns out this result is the factor of 2 is tight. And the sort of main technical new result in the paper I'm planning to focus on today is that that somehow this no regret is really a bad idea here, and if the players or the queues here evaluate the service differently, namely more patiently, then you don't need a factor of 2 capacity. It's this E minus 1 over E is enough, which is 1.6, a factor of 1.6 something. So there's 2 things I'm hoping to do today in the little time I have. Definitely to step number 1, I want to give you an intuition of what is going wrong with no regret learning. And that's going to happen in the following super simple example. And then I want to give you a little bit of a hint, but given the shortage of time, not that much of a hint of how do we prove that indeed, in the worst case, even something better happens if they are patient, if the queues are patient. So what this example illustrates is what's wrong with no regret learning, or actually, if you prefer, what's wrong with Hanan consistency, which is the same thing in this case. So there are two cues here, which both of them have arrival rate 0.51, so a tiny bit above from 50%. And we have a server that's perfect. It has service rate 1 that is always serves whatever it gets, absolutely guaranteed. The natural solution I claim, and in fact that is a no regret algorithm can allow them to do, is both of them compete for this better server. Now think about what's happening when they both go for the top server. The top server, as far as they're concerned, the server is concerned, they're pretty identical, depends on the randomness. Sometimes one is a little bit older and sometimes the other one. There will be some randomness in this, but on average, they're going to share the service rate from the server 50-50. So they're going to experience a 50% service rate. That is, they get served roughly 50% of the time, which you must notice is better than the 0.47. A 0.47 is literally a smaller number than 50%. So no regret learning algorithm, even if I feed full information to them, that is, I actually not only ask what Pradeep asked me to ask about is see other people and other people's ages and all this other stuff, but I even feed them the service rate of the queues. They just know that the other one is 0.47. It's not tempting to use it because it's a lesser service rate. So any deviation actually gives you regret. Next, I want to convince you that that's the right thing to do. Suppose you deviate. So suppose, and of course I didn't point out, but this leads to linear growth because their combined arrival rate is 1.2 and the service rate is 1. So the queues will back up linearly and there's nothing you can do about this. So what happens if one of them decides to split? So splitting means this. A little bit of the time, say 0.1%, you start actually using the lesser queue. At first sight, this looks like a move that's designed to help the other guy, because you went off to a lesser server, so the other guy sometimes has no competition, and in fact, it does feel like you have the top server rather than helping yourself. The top queue has less competition, he cannot service, and you're using this lesser server. But it turns out you're also helping yourself. Because what's really happening here is that when you went to that lesser server, you suddenly will be a bit older. And as a result of being a tiny bit older than the other queue, whenever you go back to it, you actually will end up having priority. So it turns out that this is not only a move to help your friends get served, but actually it helps yourself. So going to the lesser server is actually an improving selfish move. And what I mean here, going back for a second to the previous one, at this stage, you had a 50% service rate. The moment you go down, you actually give up on some of this, because sometimes you go to a 0.47, but the long-term effect of what you did will actually allow you to get serviced. So there is a long-term effect here that the step-by-step evaluation of how myopic the no regret or the Hanan consistent condition is not taking into account, because that was not invented for games where is a state. Here there is state, and as long as the other queue keeps cleaning faster, his packets are less old, and that gives you priority when you go there, and in fact you do get served. So I also want to give you a little bit of so what's really going on here, which I think I said that they're not patient in evaluating the long-term effect of the change. And I guess I want to show to you that this isn't just one example, but actually there is something more general going on. So here is the game we want to study. And in this case, I'm not going to study learning outcomes, and the end question, which I definitely will get to even if I didn't show you all the details of the proof, is you know, if you were giving advice to people what might be the right way of learning, I would definitely say that we show something wrong with no regret learning. That is, they should evaluate the outcome in a more patient way. Would be nice to prove positive results if the players actually learn to do that. So at the moment, we're going to evaluate a Nash equilibrium of a game, and here is the game. Every Q picks a fixed randomization over how they're going to distribute the packets with probability Pij, they send it to server J. Every run they uses the same packet. This causes a Markov chain on the queues as they, you know, send packets and have more and more packets lining up. And every queue will have the goal of minimizing the asymptotic aging rate of or backup rate of its packets. That it has low packets, that this distribution is not working for them. If it has fewer packets, then the distribution is working for them. In particular, I guess they're going to have the objective function, the age of the queue, that is the oldest packet in the queue, divided by time, and they're trying to minimize this lim sup. That's the goal of the game, and we're going to look at the Nash equilibrium of this game. You might have a lot of questions here, which I will come back to in one tiny second. That is whether this asymptotic aging rate that I claimed is actually a well-defined quantity, or whether this game actually is guaranteed to have Nash equilibria. The answer is yes and yes. I'll come back to it 1 second. I want to do next is show you one, I think, insightful example of one of these games with a Nash equilibria. So here is a game where there are 3 servers, perfect servers, each a service rate of 1. And unfortunately, 4 queues that are competing with the service of these 3 serving packets. It has a Nash equilibrium, like there is not clear what might be a Nash equilibrium here, and maybe there are better and worse Nash equilibria, which we'll come back to in 1 second. But here is one that's sort of maybe easy enough to understand. The 2 side queues are sending to the side server deterministically with probability 1, and the 2 middle queues randomize. I wrote down not the exact numbers, but the approximate numbers with 0.27 and 0.73. To be more precise, the 0.27 should have been √2 minus √3. Those are the probabilities. If I do this as probabilities, then it will turn out that all queues will clear at the same rate. And as long as lambda is above something, then they're all going to have backup. So if lambda is above something like 0.73, or more precisely exactly 0.73, then the queues will back up, which is not very surprising. Maybe it's a little bit surprising. Let's come back to that in 1 second. So again, back to what I promised as immediate problems. Is there asymptotic aging rates actually well defined? Why do we know that they're guaranteed to be Nash equilibria? And the question I meant to ask is there what's the price of anarchy? Given the short time for these talks, I want to give you a little bit of hint of the first 2 and a little bit of hint of the last one. So just as a reminder of why the equilibrium, what's the clearing rate, it's always useful to remind one what happens with 1 queue and 1 server, which is no game. It just, you know, there's 1 queue, arrival rate lambda, service rate mu. And as you well know, of course, lambda has to be less than mu if you want to survive it. But actually, because we care about clearing rates, it might be useful to actually write out the clearing rate. So a packet that gets cleared with probability mu, the expected decrease of the ages is 1 over lambda if the server succeeds, and guaranteed time goes 1 time step ellipsis. So the long run aging rate will be 1 minus mu over lambda. I can maybe say this again. If with a lambda packet rate, the if a queue gets served, then the next queue, next packet will have a 1 over lambda age younger, and that happens with probability mu, and we're guaranteed to increase the age by 1, which is where this expression comes from. So in the general case, what I need to do, and this is maybe definitely non-trivial to prove, but I won't actually prove it here, or won't even give too much of a hint to prove it, is looking at groups of packets, which I guess I can page back to that example. Sorry, far away. And here the group that I care about will be the group of all the queues together. Look at the combined arrival rate, which is I call lambda of S, which is all of the number of queues, any of this, or the probability that any of these queues will get a packet combined, and the expected clearing rate, pretending this subset is alone in the word, and this is the only subset that matters. And then I take the worst ratio of these, and that's going to be the most problematic aging rate, and then recurse on the last. This has some nice structural properties, which allows me to use the usual kind of proofs for equilibrium exist. These subsets are closed under intersection, and they're continuous in the probabilities, so I can use a fixed point theorem to prove that Nash equilibrium exists with some concentration of the probabilities. So let me spend at least a couple of minutes on the price of energy intuition and proof. Which is, I guess, was the main point I wanted to get to. So I'm claiming that this is the worst example. That is the worst example if we have n identical queues and n identical servers. In fact, the servers can be perfect as far as I'm concerned, all these mu equals 1. And what the queue is doing is uniformly randomizing. Every one of them uniform randomly picks one of the servers. It is not hard to believe that whatever game they're playing, this is an equilibrium because of the damn uniformity. If you change from the uniform behavior, but no one else changes, then of course you're not helping yourself, you're worse off. This needs a proof, but it's not hard to believe. And indeed you see that in this system, you do need an E over E minus 1 slack, because this random system is 1 over E fraction of the time every server is empty and unutilized, which is of course unfortunate for the service rate. So this is literally what we're claiming as a theorem, that this example that I have on the slide is the worst case. So I want to give you maybe 1 minute long hint of how does one go about trying to prove this. And maybe instead of really proving anything, we'll show maybe, yeah. So proof sketch will go as follows. I'm going to take any Nash equilibrium, which I can't describe or not, certainly not in a closed form of what a Nash equilibrium. It just has the properties that no Q is interested in deviating, and somehow try to make it closer to that uniform kind of distribution. And my first step is uniform in the sense that I want every server to have either the same amount of probability mass on it, or at least proportional to its service rate. And I want to claim that I can do this without using the Nash property, should that life only gets worse if I move so that every queue gets proportional packets arriving there. And then it's a not very hard lemma that once the service is proportional, so here in our example, the total probability of every server that it gets is 1. That is, it's coming from n queues and probability 1 in n. The worst case under that assumption is if they behave symmetrically. That is a relatively easy lemma to prove. The hard part is the moving to, like having a Nash equilibrium move towards this, which that is, we want to continuously deform a Nash equilibrium in a way that constantly increases aging rates to make it in this symmetric setting. And I guess instead of really giving you a hint of how we do it, or maybe giving you a small hint of how we do it. I go back to that example I showed you in the beginning and maybe show you slight the difficulty here. Is there multiple tight sets, that is aging at a maximum aging rate? In this example, these two sets are these three, as is the four combined. That is, every subset containing the middle two is aging at the worst possible rate, which makes it a rather complicated system. And every one of these queues doesn't want to change its probability distribution for a different reason, so it's a bit hard to argue with it. But one fact I didn't emphasize, though was on my slides, is that these tight sets are closed under union and intersection, which allows me to put them into level sets and use these level sets to starting from the top level to deform. So I guess I want to end with a few open questions and directions and maybe a message I hope you can take home from what I was trying to say. One is, I think understanding the price of energy in repeated games that have a state, that is, what happened in one iteration affects the next iteration, is an interesting and seemingly more difficult problem. The queuing system example shows us that no regret learning might not be the right form of learning here. I guess the two natural questions is, can we extend this to other forms of games with state other than this very simple queuing system, and whether there is a better way of learning that we can maybe recommend to the players that would do better than no regret learning does. And thank you everyone for the attention.
All right, thank you, Eva. Yeah, we'll take a question or two as we switch over, and I see in the Q&A there's a question from Kathy Zhang, which I'll read out. How is the patient queue related to the stochastic game, which is also considering the long-term reward? And additionally, will it help to introduce hidden states, e.g. to share the information of the length of the queues of each agents to help improve the price of anarchy?
Definitely, I'm happy to, like, the second question, second part is raising a very I can make interesting question, which I don't have as good an answer as I would hope, or is to make my game super simple, and maybe to answer the question that Pradeep asked in the beginning about how much information do they share with the players. I made them send back the packets. That is, the servers didn't have a queue accumulating servers there. Painfully, I can't even extend this result if I allow every server to keep a minimally short queue that it can keep up to 4 packets, and will serve them eventually. And only sends back the 5th and 6th and 7th packet, because by then it ran out of space, which will be a much more realistic version of how actually packet processing works. And it should help, actually, even without feeding information. The fact that your packet can stay there and get served tomorrow, that might be perfect for you, definitely better than being sent back. And it should help the price of energy, and would be nice to be able to prove that, and maybe even prove the difference with or without information. And I guess in some way, this is also the answer for the first part of the question. In the stochastic queuing system, they tend to allow the queues, the servers to actually have queues and within the light, which made it a much more simple game to study in the game theoretic setting, but different than the stochastic game.